can see you all. Wonderful. Well, good afternoon to you all, or good morning, depending on the time zone that you're joining us today. And welcome to the Impact research seminar, where we're listening to emerging and established leaders in the field of imaging. So it's a great pleasure today to present to you our talk, which will be delivered by Dr. Kay Morgan. Before we begin the talk, I'd like to acknowledge the tradition and custodianship of the traditional owners of the lands in which we're all joining on today. Today, I'm actually in Adelaide, which is the lands of the Crysta people, but I know that you'll be joining across many different First Nations lands. So as by way of an introduction, Kay works in X-ray imaging in the School of Physics and Astronomy in the Faculty of Science at Monash University, and she's currently a Future Fellow awarded by the Australian Research Council. Prior to this, Kay was also the Vesky Postdoctoral Researcher Fellowship awardee, spending several years at the Technique University of München as the Hans Fischer Fellow. And this followed her very early career success as an ARC DECRA, which was awarded after her PhD. So Kay works in the field of X-ray optics, which is developing new methods of imaging that reach new scales of resolution, speed, sensitivity, and across new contrast modalities. And one of those contrast modalities is phase contrast X-ray imaging, which examines the changes in the X-ray phase rather than the X-ray intensity, which helps reveal soft tissue structures like the airways that are not actually seen readily in conventional X-ray imaging. Another area that Kay works in is in dark field imaging, which reveals subpixel unresolved structures that scatter the X-ray wave fields. So Kay is working on both developing and extending these methods and applying them to new research questions. Her imaging is performed largely at the Spring 8 synchrotron, the Australian synchrotron, and the Munich compact light source. So without any further ado, over to Dr. Morgan.
Thank you so much, and thank you for having me. So today I want to tell you about a new approach to imaging the lungs, X-ray dark field. So I'm going to break this up into a few little chapters. Hopefully there'll be at least one or two of interest to each of our diverse members of the audience. So I'm going to start off talking about how is this relevant to the Impact project, which is looking at taking phase contrast imaging into the clinic, firstly for mammography and then potentially in the future for the lungs. I'm going to talk about what exactly is dark field imaging, some examples where it's been applied to the lungs, and then some new methods we've been developing here at Monash to capture dark field. So the project 4 of the Impact project, the one that I'm leading, is focused on establishing the feasibility of propagation-based phase contrast CT for lung cancer imaging. And so there's a few clinical motivations for this. First of all, can we pick up a lung cancer? Can we see something in a whole lung image that indicates that there might be a tumour? And then can we potentially get some more information about any potential problems by doing some high resolution imaging of suspicious areas? So maybe something's being picked up, but can we image it to avoid having to do a biopsy? So the core approach that we've started in Project 4 is doing phase contrast imaging. So we can see here some lungs. They've been each image in this rotation series is at the same point in the breath cycle, but you can see the heart beating there as well. And the phase contrast that we get by moving the detector back some distance means that we see this kind of speckle pattern from the lungs. And this speckle pattern gives us extra sensitivity to all those air sacs in the lungs, which means we can reconstruct really detailed CT slices like this one here. And so the core approach that we've started is, can we have a look at these kind of really sensitive CTs to better understand where the lung cancers are? So we've started off with some first imaging of lungman, a phantom, which is conventionally used in just normal radiography, where we're looking at the absorption of X-rays. But we've looked at, can we use this particular phantom also for phase contrast imaging to pick up tumours. So some very preliminary images here. We can see this kind of black outlining of each of these little vessels in the lung phantom is due to the phase contrast, which really makes them much more easily visible than in a conventional X-ray. So we can see one of the tumour inserts here, perfectly spherical, but this is what comes with the lungman. We can also see a slightly smaller one over on this side. And there is an even smaller one somewhere around here, which is, of course, quite hard to see in projection. But with some of the CT reconstructions that we're working on, we should be able to see even these smaller features much more easily. So just a quick little preview of some of the CT sequences that we've been collecting to start off this part of the impact project. So this core approach does rely on us being able to detect these phase effects, this kind of speckle pattern from the lungs. And to do that, we need relatively small pixels because these effects are quite local. It enables us to get this very detailed image, but it does mean that there's a large radiation dose associated with the imaging, which is something we're working on getting down. And so we're also interested in techniques that can avoid having to use quite so much dose to the patient. And one approach that we're considering is dark field imaging. So this is useful because it provides information about this microstructure that we're seeing here, but without having to directly resolve each of those structures individually. So this brings us to chapter 2 of the talk, what in fact is dark field imaging. So some everyday examples. Here we've got some images of a tube of water and a tube of sugar. So in a conventional attenuation-based image, they look pretty similar. Maybe it's a little bit more textured with the sugar, but it's hard to tell the difference easily. In a dark field image, we see not really any signal from the water. We see some signal from the edges of the tube, but we see a whole lot of signal from the sugar. And so whenever we have this kind of highly textured sample where it's very porous or very grain-like, that's where we see a dark field signal being created. As another example, a pair of glasses inside a glasses case. In the conventional attenuation image, we see the screws that are metal, so very absorbing. We can see some of the plastic structures. If we do a dark field image, we get a huge signal from this tissue, which is wrapped around the glasses. And that's because there's a lot of little fibres that are in this tissue, and they are creating this dark field signal. Finally, a pencil sharpener. Again, the highly attenuating metal parts of the blade and the screw show up well, as does the plastic outside. But in the dark field image, we're sensitive to the tiny grains that are in the wood shavings. And so we see the shavings that have come off the pencil with a lot of contrast. So really quite a complementary technique to conventional imaging that's accessing a different kind of contrast. So how does this contrast come about? So if you imagine there's a very small X-ray beam that's going into whatever object it is that we want to image, and that object is full of little structures. So it could be those sugar grains that were in the first tube, it could be the fibres in the tissue, or the fibres in the wood of the pencil shavings. And so when this beam comes in, when it encounters one of these structures, it could go straight through the middle. If it lands slightly to one side or the other, it could be refracted so that it changes the direction the light is propagating. And if the structures are very small compared to the wavelength of the light, we might also just see some diffraction of that structure. And so that means that there's kind of a range of angles that we might see the light coming out of this structure or diffracting off this structure, depending on, because it's got some finite width of the beam, exactly what part of the microstructure is encountered by the beam. We then see that it could run into another microstructure. We could see, again, another spread of angles from that microstructure. There's several more that can then refract or diffract the light even further. And so there might be that one particular photon, if you like, a package of light goes along this path here, but there's many, many such paths that add up to this kind of distribution of where the light could end up. We can imagine that this is if we took an intensity profile across the beam here, so it's low intensity, high intensity, and then low, so low, high, low, then we could say, as this beam goes through the sample, this spreads out. And by the time we come to the other side of our sample or our patient, we see that there's quite a wide spread in the position of the beam. And also it's not quite as bright because the light that's here has been diffused and spread out to other positions. So this kind of leads to this picture of the different kinds of contrast that we can get with modern methods of X-ray imaging. So if we imagine this very small beam, we could call it a beamlet, is going through a sample that's attenuating. So it's dense, a metal or a bone. We'll see the strongest effects. That intensity profile, how bright the beam is across the beamlet, is going to be decreased in intensity in the case of this attenuation. And that's how we get an image, a conventional image where the bones show up nicely. We can see that this beamlet might be refracted so that it's going in propagating in a slightly different direction after exiting the sample. We can imagine this as a kind of drift of the beamlet. As you move down further downstream of a sample, that this drifts sideways more and more. And this gives us a differential phase contrast here. And so this is very sensitive to soft tissue features. So we can see the airways in this image. This is of a mouse that's sitting in a plastic chair. And we see that even things like the ears showing up really clearly. And finally, we can imagine that this tiny beamlet is going to be diffracted and multiply refracted, as we described here, to spread out that beamlet so it becomes wider. So these three kind of distinct actions that are giving us three different kinds of image contrast. And so in this dark field image of the chest, we see that the lungs are really appearing very clearly. There's lots of tiny air sacs that make up the lungs. And so those little air sacs are creating a strong dark field signal. We also see some signal from the fur of the mouse, particularly where there's lots of hairs compacted under the arm. And there's also a strong signal from this piece of micropore tape, kind of like a masking tape, which is holding the hand in position on the chair. So the lungs clearly seem like the best candidate of the organs in this part of the body, at least, for dark field imaging. We can quantify these effects. We've got some nice equations that we can do that for attenuation and phase. And we're looking at how can we do that for dark field as well? How can we relate the properties of the sample, for example, the size of air sacs in the lungs, to the strength of this dark field effect? And there's a paper that's just been posted on arXiv recently from David Paganin, Daniele Pelliccia and myself, that's also looking to come up with some equations that can do this for dark field. Okay, so the lungs look good. Let's have a look at some examples of dark field imaging of the lungs. So I just wanted to quickly explain the setups that can be used to collect this kind of image so that you have an idea of the associated complexity of the various approaches. So one approach, which has probably been used the most globally for dark field imaging of the lungs, is using a grating interferometer. So in this case, there's two gratings placed one after the other as the beam travels through one, then the other. And this means that the X-ray beam is split up into lots of little beamlets, like we were describing before. And when these two are lined up perfectly, we'll see that they'll go straight through to the detector. But what we actually do is we scan one of the gratings. So this second one moves sideways, which means that at some points, the light that's come through the first grating is going to fall exactly in a gap and give us high intensity. But at other points, the light that has gone through the first grating is going to be landing on one of the lines in the second grating, which means that we get low intensity. And so the first step in grating interferometry is to collect a reference scan like this, where the position of the second grating is stepped through one whole period of that grid, so from one grid line across to the next, and record the intensity that's seen at every single pixel during that process. So this provides a kind of reference for what would happen if there's no sample in the beam. We then introduce a sample to the beam. So this is the same mouse. And we see how does this stepping curve change due to the presence of the sample. So obviously where the bones are, it's much darker. So we would see that the total intensity that you get through is always going to be less. We're always going to have less light coming through. And so we can get the attenuation image that we saw. That's doing something interesting. The attenuation image that we saw here from looking at that mean value of the stepping curve. We can then look at how does the stepping curve move sideways. So if the X-ray beam that's come through the first grating has been refracted so that it's now propagating in a slightly different direction, it's going to find a gap in the second grating at a slightly different position to what it did previously. And so we're going to see that that moves across. And you can kind of see it by looking at the edge of the plastic chair here, that the bright dark bands aren't quite lined up anymore. And that's because there's been some phase effects there that have shifted the direction that the light's traveling. We can also look at the amplitude of this curve. And so if we look at the lungs, for example, we see that the intensity there is not changing significantly as we step that second grating. Outside, we see big changes. It goes from dark all the way through to bright, but inside it stays quite still. And that's because the light that's gone through the lungs has kind of spread out so that it's not really a thin beamlet anymore. It's a diffused beamlet, and it's getting through the gaps in the second grating basically all the time. And so that means that we're not going to see such big variations across the stepping curve. And so typically a scan would capture at least 7 points, 7 positions of the second grating, images at all those in order to then reconstruct a dark field phase and attenuation image. And you need 7, whether you wanted all 3 of those or if you were just looking for a dark field image. So the earliest examples of applying a grating interferometer to look at the lungs was on excised lungs. And so this was the group at the Technical University of Munich, where I spent some time. And so they took both attenuation-based images of these lung samples and dark field images. When you just have a lung, it looks kind of similar. You don't see such a difference between the attenuation and the dark field. But if you do plot the intensity values, so take all the pixels in the emphysema images and plot how much dark field you have on the y-axis and how much attenuation you have on the x-axis, you do see a difference between the mouse lung that has emphysema in red and the healthy lung in blue. So in emphysema, the air sacs in the lungs break down. And so you can see here from these histological slices that there are many fewer air sacs and they're much bigger. This means it's hard to take up oxygen, so it's quite serious. And so this difference can be seen in how much dark field is observed. So the more structures that you have, the stronger the dark field will be. And so when you've got less structures, you will have less dark field. So the red's sitting slightly higher than the blue here. They then built a small animal scanner and imaged living mice. And so you can see here now there's a bit more complementarity between the attenuation images at the top and the dark field images on the bottom here. And so again, here they looked at a fibrosis model. So we were seeing that the lungs in this histological slice are becoming quite clogged up. The air sacs have been inflamed. And so we're actually getting less structures in a projection, which means we're getting less dark field compared to the healthy mouse. So this was also applied for lung cancer in the animal model. And so we see, looking at the conventional image compared to the dark field, it's kind of hard to see any of the lung cancers in the attenuation image. But when we look at the dark field, we can see these kind of dark spots that correspond to tumours which are observed in the histology. So when there's a tumour, that means it's blocking up the air sacs. We don't have the presence of many air sacs there. Instead, we've got a solid mass, which means that there's less dark field. And so it shows up as this quite strong shadow in the dark field image. During my time there, we also looked at capturing time sequences of dark field. And so we can see here is a mouse that's breathing in and out. And if we actually trace the intensity in the dark field image, we see that it changes through the breath. So when the lungs are most full, they're going to be a kind of darker colour because the air sacs have expanded. We don't see so many air sacs in projection, and so we see less dark field signal. And so if we trace that with time over the breath, we see that dip. And so that's useful in terms of trying to figure out how much each of the air sacs, so alveoli in the lungs, are inflating to measure how are they elastic, are they healthy. And it's also useful in informing what point in the breath is going to be the most useful for a diagnostic image. Is it best to breathe in and spread out the features of the lungs, or is it better to breathe out so that you get a stronger dark field signal that it's easy to pick things up? And so this led on to, they've done quite a lot of actual diagnostic imaging in a hospital in Munich using this technique. So they've built a human-sized grating interferometer and captured dark field images of a couple of hundred patients over the last 4 to 5 years. So here's one example. So this was looking at emphysema. In the conventional image, we see the bones quite strongly. In the dark field, we see the lungs. And we see that the dark field signal towards the top of the lungs isn't quite as bright. And so when this is compared to a computed tomography of the lungs, we see that using a densitometry measurement of that CT, that there's emphysema in the top part of the lungs here, which is matching up with that decreased dark field signal. This is even more apparent if we compare to some healthy lungs. So here we've got the healthy lungs, the emphysema lungs, where we see that there's much more even dark field signal because the dimensions of the air sacs in the lungs are much more even across the CT data set. We also clearly get a very reduced dark field signal in the presence of very severe emphysema here. So this was the first study that they've published, but there's been a number of studies since looking at the severity of various lung diseases. So here we've got COPD. You can see a sequence of different patients, many different sizes and shapes, but that clear change in the dark field signal depending on the severity of the lung disease. Another study, they looked at COVID-19 and again saw a decrease in dark field when there's either inflamed or blocked lungs. I don't have time to talk about all of them, but if you'd like to hear some more information, in a few weeks' time, Henrietta Bust, who is a PhD student from the group in Munich, will be giving a talk on this. So she's visiting Monash University for a few months at the moment. And as part of the Imaging and Optical Physics seminar series, she will be talking about this on the 27th of April. So do feel free to email me for details and a Zoom link if you're not already on our Imaging and Optical Physics seminar list. Another approach that's been used for dark field imaging of the lungs, which was actually first started even earlier than the grating interferometry work, is using a crystal. So this work was led by Marcus Kitchen, who's here at Monash. And instead of using gratings to analyse how the sample changes the X-ray wave fields, he used a grating, a crystal. So they call it a crystal analyzer. So what happens in this kind of setup is that the crystal is set up so that the light is coming in at just the right angle to diffract off the planes of the crystal and land on a detector here. And so this can be done either in a kind of reflection mode, which is called Bragg, or allow geometry we see here where it's going through the crystal. So the crystal is rotated, just like we stepped the grating. And instead of collecting a stepping curve, a rocking curve is collected to look at how well is the light reflecting off this crystal. And it will reflect particularly well at one particular angle, which will be this peak of the rocking curve when it's lined up just right with the incoming light. So this gives a kind of reference. Then the sample is placed in the beam and that same rotation of the crystal is repeated. And so this means that we can look at, is the wave field still coming in at the same angle, or is it shifted slightly? Has it been refracted by the sample, phase effects? And is there a big spread in the angle of the wave field coming into this crystal, which will spread out this rocking curve in a very similar manner to we saw with the stepping curve with the previous technique. So this is, again, just like with grating interferometry, multiple images are taken at different positions of the optics, which then enable you to extract the attenuation, differential phase and dark field images. So Marcus used this technique to look at, can we quantify these changes in the lung microstructure using the dark field? So using the differential phase image, they calculated the thickness of the air that is in the lungs in mice, used the dark field image to then work out
Is this frozen for anyone else?
Yes. Yeah, for me as well.
Yeah, I think we might have just lost Kay. Just give her a minute to come back online. Amazing technology description from Kay, and yet the internet is letting us down. Great, thanks, Linda. There we go.
Okay, I'm back. Which slide did I get to before the edgy roam dropped out? This
Yep.
one? Yep.
No, yep, we heard you talk that one. Yeah. So
the next one?
Yep.
Okay. So we can take the total air thickness calculated from the phase image, divide by the number of air sacs that are in the lungs to get how big each of those air sacs are. And so you can see with the different degrees of emphysema that these air sacs might be very small or much larger. And so Marcus was able to quantify this from these combination of dark field and phase images. Could then produce a kind of histogram of what's the size of the airways across the lungs. And so you see with the emphysema that they tended to be much bigger with those airway walls breaking down. Okay, so first question is, can dark field imaging help with lung cancer? It seems pretty convincing that it can be quite useful. But how can we easily capture these X-ray dark field images? So both of these techniques, and I've talked about, require a relatively stable environment. You need to be able to do the reference scan and the sample scan one after the other and have them match exactly, which can be tricky in terms of having a really stable setup. And also there's multiple images required to extract these dark field images. So a question that we're looking at here at Monash is, can we develop new methods to capture these X-ray dark field images? We might be able to employ at the Imaging and Medical Beamline here, the Australian Synchrotron. So this brings us to chapter 4, new methods to capture the dark field images. So there's two kind of methods that I want to talk about today. And the first one is using a patterned beam. So I showed you this diagram where we've got these kind of tiny beams that are going through the sample. And so the idea of a pattern beam is to say, well, let's just have lots and lots of these tiny beamlets all next to each other and observe how they are drifting and diffusing directly without having to actually use any optics to do that for us. So the setup is simply that the X-ray beam goes through some kind of object that will pattern the beam. So it could be a grid pattern, which is what we see here. And we look at how this grid pattern is kind of distorting, how it's drifting around and how it's blurring out in order to then reconstruct those phase and dark field images. And so most of the work to date has been looking at the phase images. So how are these dots kind of squeezed together or spread out? But dark field imaging is where we're kind of looking next. We don't have to have a perfect grid to do this. We can also use something like a sheet of sandpaper that will give a reference pattern like this. And we can similarly track how that pattern is shifting around when the sample is introduced. So this has some advantage in that we need to capture one reference image of the grid or sandpaper by itself, but then we only need to capture one image with the sample in place to be able to extract the phase and dark field images, unlike the methods that require multiple exposures. So Ying Hao here at Monash, as part of her PhD, has been looking at how can we extract a dark field signal by looking at how each of these little beamlets here are blurred out. So this region is perhaps blurrier than this region because there's some structures in the sample that are creating a dark field signal. So she does this in a kind of direct method where she looks at a small window in an image of only the grid and the corresponding window in an image of the grid and the sample. And so when the sample is present, we see that the intensity is reduced due to attenuation, but also that grid pattern is becoming a bit blurrier, especially at large propagation distances, so large distances from the sample to the detector that's capturing the image. So she can look at how blurry this is by looking at these small windows with a cross correlation, which compares that local part of the two images and see how much blurry it is to extract this kind of dark field image here of two tubes filled with tiny spheres. And we can see that that's also going to be complementary to the attenuation image, which you can collect by looking at how much the intensity reduces. So Ying has done this at multiple distance and characterised a whole lot of different size samples to look at how can we use this dark field signal and the attenuation signal to work out the number or the size of microstructures such as air sacs in the lungs. Michelle Crowan has also been working in this direction. So she's looked at the specific case of what if that blurring that the sample is introducing is not symmetrical? What if it's more in one direction than another? So if we look at these two images here, we see that the lower one has been blurred more horizontally than it has vertically. Those horizontal lines have kind of become fuzzier than they were in the grid-only image. But, sorry, the vertical lines are more blurry, but we can see these horizontal lines are quite strong. They haven't been blurred much. And this happens when you have some features in the sample that are quite small, but only in one direction. So something like fibres or threads here mean that the beam is going to be scattered a lot horizontally, but not vertically. And so Michelle uses a cross-correlation approach to locally analyse both of these two images to then extract how the intensity is reduced for a transmission image, here of a slice of lemon, how it is shifted around. We can get the differential phase image, and then we can get a colour dark field image, which is telling us about the particular angle of the fibres in the sample. So here, the rind of the lemon has the fibres going around the lemon, and so we see that that signal changes colour in terms of the orientation of that dark field as we go around the lemon here. I think it's kind of nice too that we see this signal is just from that white part of the lemon. So the kind of outer skin here, where there's the kind of juice pockets, we don't see that strong dark field signal. And because we only need one exposure of the sample to extract these images, it also means that Michelle can reconstruct time sequence images. So here she's got the attenuation and the dark field of some carbon fibers that are soaking up some water over time. And so this means that we see less dark field signal because the water and the carbon fibers are quite similar. So there's less interaction with the X-ray wave field. And so this is kind of promising in terms of applying this kind of technique to the lungs breathing, for example. We've also looked at how can we extract these signals by looking at the whole images all at once. And so this has come out of some work that David Paganin and I did in terms of coming up with a model for dark field. So we came about this model by looking at this X-ray beamlet going through our sample, looking at how it's going to drift sideways due to the phase properties of the sample, and how it's going to be diffusing due to the dark field properties of the sample. And that we'll see these kind of effects changing as a function of propagation distance. So that width will change at a given distance from the sample, and the drift of the beamlet will change depending on the distance from the sample. So we can talk about this intensity profile as a kind of probability density function, in that it's describing the probability of where the next photon is going to land to build up this distribution. And we can think about a drifting probability density function and diffusing probability density function, which we have equations for already. And so we can look at how these equations can then be employed in the X-ray setting. So if we add both effects into one equation, we get what's known as the Fokker-Planck equation, which has been used quite broadly in a number of areas in physics and mathematics. And we're just going to adjust it so that instead of talking about how this function is changing with time, we talk about how the intensity that we see in the image is changing with the distance from the sample. We can then say, well, it's going to drift with a particular kind of velocity that relates to the phase gradients, and it's going to diffuse with a velocity that's related to the dark field that we see in the image. So we can use this equation as a basis to retrieve dark field. And so Mario Beltran, who's a postdoc here at Monash, has been looking at using this kind of basis in this imaging where we use a kind of patterned beam. So we collected some images using a grid, and also some images using a speckle pattern of a test sample made up of some PMMA here, which shouldn't create a dark field signal. It's like a block of plastic. It's very similar X-ray properties to soft tissue. We then have a wooden skewer, and then a little tube that's full of tiny spheres, so kind of like the air sacs in the lungs. And so if we zoom into that part at the end of the tube, we see that the grid pattern that's being shone through the sample is getting blurred out behind those tiny spheres, but it's quite sharp around the outside. So Mario's approach uses this same kind of Fokker-Planck equation, where we're saying that this X-ray beamlet is going to be drifting or flowing due to phase effects, and it's going to be spreading out or diffusing due to dark field effects. And so he takes a kind of reverse flow approach, where he says, how does one image flow and diffuse into the other image? So I'm not going to go through the details of mathematics, but I'll put it here there's a few members of the audience who might like it. The key steps that we do is to first recover the thickness of the sample. And so this is basically done by taking the sample image, dividing out the reference pattern. We don't want that immediately. And then doing a transport of intensity kind of phase retrieval that we'd normally use for propagation-based imaging to get the thickness of the sample. So this is assuming that it's a single material, but this is also quite flexible assumption. It seems to work all right, even if a sample like ours is clearly not made of the one material. The second step is to say, okay, we've got the thickness. Now we can calculate how much the sample is attenuating the beam and how much the sample is creating phase effects. So we can use the thickness to work out the gradient in the thickness in X and in Y, which then go into creating this flow term. And then we can create the flux, how much is getting through. So our equation then says if we add these two together, we should just be left with the diffusion or dark field term, which looks like this. The final step is then just to get rid of these other terms that are around our dark field that we want. And so we need to undo this second derivative and divide out the constants to get an image of the dark field. And so we see a strong dark field from the wooden skewer, also from the spheres that are in the tube, just up to the level where they're sitting. And if we zoom in on the point, we can see that's that the plastic tube itself doesn't give the dark field, only the tiny inside. And so we can do that with the speckle or with the grid, which is a slightly better contrast because the grid is better contrast. Talking about contrast, this technique has proven to be very robust when we look at reducing the exposure time. So if we use the image of the lemon and go to very short exposures such that you can really barely see that reference pattern, that speckle, compared to in the reference image, this technique is still able to pull out the dark field contrast out of that, which is promising for low dose imaging. The second method I want to talk about is what happens if we don't want to use any optics at all. Make it as simple as can be. Is this possible? And so in this approach, we've been looking back at some previous work, and we saw after we'd done this work, a paper way back in 1999, one of the first examples of phase contrast imaging. And so this was from the Japanese synchrotron, and they were looking at if you increase the propagation distance, we see these phase effects. So we can see the lungs much more clearly than in a conventional attenuation image. And if we zoom right in on this part of the lung, we actually see there is some difference between the thickest part of the lungs and the thinnest. So in the thin parts, we see that there's a lot of this really highly detailed speckle from the lungs. But in the very thickest part here, it's kind of being blurred out. And so in a sense, the lung here is kind of acting as its own patterned illumination. That the sample is kind of the reference pattern that we're looking at, how much is it blurred out. And so the question is, can we use the texture that's just created by our sample itself to analyze how strong a dark field signal is? And this kind of local blurring was also described in a publication also quite some time ago by a member of our audience, Yakov Nesterets. So we did some experiments looking at some tiny spheres in a plastic tube, one of our favorite samples, and we captured images at various distances away from the sample. So we can see as we increase the propagation distance that the phase effects increase, but also we see this significant blurring behind the very thickest parts of the sample where we're looking at a lot of those tiny spheres in projection. And so if we compare the kind of the edge of the tube here where there's only a few spheres in projection, it still looks quite sharp, but in the center here, it's getting quite blurry. And so Tom Lethem, as part of his PhD here at Monash, has written out this Fokker-Planck equation that I just mentioned for those two distances, and then said, okay, I want to solve for the thickness of the sample and also for how much dark field there is. So if I'll take the image at two different distances to solve for these two unknowns. This is one of the equations that came out to reconstruct the thickness of the sample. And so because this, the phase and the dark field effects, they change separately in different ways to each other, I guess, with propagation, then we can separate out how thick the sample is. This is the reconstruction construction. It's actually slightly sharper than with a conventional transport of intensity retrieval. So that's the conventional retrieval, and then that's with this new approach. So hopefully that's coming through Zoom. This is with the conventional single distance, and then this is at the lower distance, sorry, at the larger distance, still retrieving that thickness. So we're kind of also accessing higher resolution by taking into account that there might be some dark field effects within the sample. We then say, okay, if this is the thickness, let's reproduce the image that would be seen if there were no dark field. So we can use models that, like the transport of intensity equation, that take a thickness and tell us what the image would look like. We can then compare that to what we actually observed, which was this. So we can see here that we would expect there to be a lot of detail in these thickest parts if it weren't for the dark field effects that are blurring out the contrast in the center of the image here. So when I say compare, the mathematics that comes out is that we actually literally take the difference between them. So we take the image that we observed and subtract this calculated image, and that gives us something like that. And then this is simply, to get the dark field, we simply then just need to undo this second derivative and divide out the attenuation, and we get an image like this. So a lot of dark field where there's a lot of spheres, and then less dark field here where we had some solid objects inside as well, which of course are quite attenuating, but not creating a strong dark field signal. So in the attenuation image, we see that complementarity. Okay, so there's several new dark field X-ray imaging methods coming out of the group here. We've kind of published the proof of principle methods and results on these. There's fewer exposures required than grating interferometry or ABI, so there's some promise in employing them in that way. We can use both propagation-based and single grid setups very easily at the imaging and medical beamline at the Australian synchrotron. And indeed, I believe all of these methods were tested and shown to work at the IMBL. So we're going to look next at how we can employ these in lung imaging and how we can quantify things about the airways like the air sac size using these methods to really quantify lung health. I didn't have time to get into all of it today, but I'd also see some work by Samantha Allu from the University of Canterbury, who's used this same Fokker-Planck equation to do some high resolution based imaging using multiple positions of a sandpaper reference. And also watch out for a new approach where you'll see some results from Janis Allers in an upcoming impact seminar. So in conclusion, dark field X-ray imaging, I believe, could be of benefit to the impact project by revealing the presence of the microstructures. This dark field imaging is really well suited to the lungs, and we hope that some of the new methods that we've been developing can also equip these studies. That's it from me. Over to you guys for questions.
Thank you so much. Proverbial big breath in there, deep breath with all of the amazing work that you've been doing there, Kay. Thank you. I was just wondering if we do have just a couple of minutes for some questions. Do we have any questions for Kay? You're welcome to if you just want to stop sharing for a minute, Kay,
yeah, sure.
Just so we can see the Brady Bunch file. Lots of claps there for you. Please just raise your hand, or you're welcome to unmute yourself and just shout out your question if you have a question for Kay. Kay, I'm just going to ask you a very, very easy question. And I'm just going to ask you how you got into this area of imaging.
Right. So I studied science and engineering as a double degree and did some MRI imaging in my engineering towards the end of my degree. And I really enjoyed, I think I'm a very visual person, like images. And I also liked that it was a field where you could help healthcare without having to touch anything with blood, because I'm not at all good with that. So I love the black and white X-ray. It's where I can bring my my capabilities to help out healthcare. Yeah,
the beauty of the black and white images. Do we have any further questions for Kay?
I may have a question.
Please go ahead, Tim.
Kay, as I understand, the Pfeiffer group recently reported a method for extracting dark field imaging from their grating interferometry scans without stepping, so just from a single image projection in tomographic mode. Could you comment on that? And if you know that one, how does it work?
I'm not sure if I am on top of which paper it is you mean.
There is a couple of recent papers, one in PNAS, I think, in 2022, and one in Proceedings of SPIE with Gushchin, the first author, where they describe how they use the conventional CT scanner with their gratings added to collect dark field CT of patients. And they acknowledge that due to those limitations, it's of course very difficult to do stepping in that environment. So they claim that they are now able to do it without stepping.
I know, so with the projection scanner they have at the hospital, instead of stepping the grating across, they have the gratings purposefully misaligned so that you get those big moire fringes that we saw, and then they actually scan the gratings up the patient instead of kind of stepping them one versus the other. They have them kind of offset and then just scan them across the image so that you have a bright and a dark band still landing on every pixel at some point in the acquisition. But instead of, I guess, some discrete images at different stepping points, it's each pixel gets to experience that at a different point in the scan of the gratings going past the detector.
But it's still an additional degree of freedom, right? They still need some movement.
Yes. Yes.
Scanning both gratings at the same time.
Yeah, exactly.
That's our technique.
Yeah.
But in the paper that I've seen, it's of course possible that I misunderstood it, but my impression was that they somehow managed to get dark field signal from a single image without any scanning or stepping.
Yeah, I know they've done some work at the DESI synchrotron with phase grating, so very similar to the work I was showing from Ying and Michelle, where they've just used some structured illumination and extracted from that single exposure. Although I think they have preferred to do multiple positions to improve the spatial resolution.
Right.
But yeah, I should check that I've caught these papers you're mentioning.
Okay. All right, thank you.
Okay, I was just interested.
Thanks so much, Tim.
I was going to ask with the cone image, what object was inside the cone, which was showing up as a dark area in the.
Of which image? Sorry, could you add a bit more?
What was in the cone image?
Okay. Yeah. So it was just it was 6 micron plastic spheres. So lots of tiny spheres. So it's kind of the inverse of the lungs, I guess. So lots instead of having air gaps in a solid, it's like solids with air gaps. Yeah.
Do you think you can get improved tissue contrast, with fatty tissue, for example? Or, so you're going to quantify the lung health, for example. So do you think there's some ways to improve the contrast of soft tissues?
Potentially, where we see the most contrast with the soft tissues is from the phase effects. So how the different soft tissues change, I guess, the direction the X-ray waves are propagating. And so particularly by combining with CT, then we can extract soft tissue features like the heart and in the abdomen, all the various digestive organs and things, that we see more visible effects from the phase than the dark field. But potentially there are, whether there's other kinds of tissues out there that do have kind of fibers, or there's been some work looking at dark field signal from the neurons in the brain effectively. So looking at where's the kind of the flow of those neurons that can create a kind of dark field signal. So I think the scope. Yeah.
Thank you. I think we've run out of time for any further questions, but please give a virtual or real round of applause for Kay. Thank you so much. A fabulous presentation, beautifully put together and very visual. So you've hit your target there. And thank you to everyone that's joined our Impact Research Seminar, and we will see you again next month. So good afternoon to you.
I want to get some question because, like, sort of for image